Welcome back after the short break. Before I go into the next topic, I must say here that this calculation of the C in, I did a small mistake here. It should be 135 because C in equals to C pi plus C mu into 1 plus 204, and so here we do have 5 and also here we do have 10. So, I missed this 10 part. So, 10 plus 1025. So, that gives us 1035 picofarad capacitance. So, it should be 1035. This calculation remains the same. Okay. So far what we have discussed that the advantage of cascode amplifier with respect to standard CE amplifier, and namely what we have seen is that in case if we are retaining this passive element for both the cases, then gain wise we do not get much advantage. But then what we have seen that in case if we have the input resistance and the source resistance together forming a significantly low frequency pole due to this large value of the C in, then we have seen that the cascode amplifier it is giving some advantage. Now, it may be a situation where this resistance it may be small, or whatever the cutoff frequency we are obtaining by this R s and then C in and R in, that may be beyond the upper cutoff frequency defined by R c and the C L. So, for such case you may say that then what is the advantage of cascode amplifier? In fact, cascode amplifier it is having two types of advantages. One is extending the bandwidth, as we just now we have discussed, particularly in presence of significantly large value of the source resistance. The other advantage which is commonly used is that the increasing the gain drastically. So, to get the higher gain, so far whatever the example we have considered R c, it was only 2.8 K. So, the increasing the capability of the cascode amplifier to increase the gain, it has been blocked by the low value of this R c. Namely, if we put a cascode amplifier, then its output resistance it is quite high compared to this passive element. So, to demonstrate the capability of the cascode amplifier to increase the gain, first of all let you consider a different situation. Instead of having this R c, if you put some active circuit there, probably then the advantage of the cascode amplifier, particularly for enhancing the gain, it will be quite prominent. So, to demonstrate that, in the next slide what we are going to do, we will be getting almost the same numerical problem, except we do have a change here. Particularly if you see the value of this R 3, instead of 2.8 K, now we are going to take a big value, say 10 mega ohm. On the other hand, since we do have 12 volt supply here, and if we are expecting this R 3 it will be supplying the entire 2 milliampere of current, obviously then drop across this resistance it will be quite high. To avoid that problem, we consider this I bias. So, I bias it is supporting this 2 milliampere of current. So, then you may say that why do you have this resistance at all? Well, for all practical purposes, while you are implementing this circuit, it may be having finite conductance of the current source, and whatever the value you have taken here, it is feasible, particularly if you implement this part by something called cascode current source. So, later we will be talking about the implementation of the cascode current source. For the time being, let me assume that the bias circuit we do have here, it is having two parts. One is 2 milliampere of ideal current source in parallel with 10 mega ohm resistance, and rest of the things we are keeping same, namely R 1, R 2 and then R 4 and so and so. And all the bias all the device parameters also we are retaining same. Sorry, this should be BB 2. So, what we are expecting from the lower side, as we have discussed, based on the resistance here, based on the R 2 and R 4, the current flow here, quiescent current flow here, it is 2 milliampere. The voltage here, it is 0.6 volt DC. The voltage here, it is 1.2 volt. So, the voltage here, it is 0.6 volt, and the voltage coming here, of course, we have to see what will be the corresponding voltage. In fact, if you see the value of the resistances here, and if I say that the current here, it is 2 milliampere, it is getting supported by this bias current, then natural question is that if the current flow through this R 3 it is 0, then drop across this one it will be 0. So, naturally the output voltage it will be 12 volt. On the other hand, if I consider practical circuit, and let me use the analysis, slight analysis here. If I consider the resistance of this part, in fact, this resistance equivalently you can say the value of this resistance, it will be roughly GM 2 R O 2 multiplied by R pi 2. If I ignore, say, or if I consider this node, it is connected to ground. So, if I calculate this value, of course, for DC we cannot say this is ground, but for the time being let me tolerate such kind of things. And if you do so, the corresponding, in fact, this R pi is coming in parallel with R O 1. So, whatever it is, if I consider this resistance here, it is GM 2 R O 2 multiplied by R pi of transistor 2 plus maybe smaller entities over which this term it is dominating. And if you put the numerical value here, particularly if I say this is 1 by 13, this is R O 2, it is 50 K, and then R pi 2, it is 2.6 K, that gives us 10 mega ohm. Okay. In fact, this is the reason why we have picked up this 10 mega ohm. It is not only feasible, but it is also a meaningful value. And if I consider the practical value of this resistance, then whatever the little current it will be flowing here, that current will also be consumed by the equivalent resistance there. As a result, this R 3 and then whatever the resistance we are expecting here, since they are equal, so that will make this 12 volt, and the ground here in fact getting divided by R 3 and this equivalent resistance, and hence the voltage, DC voltage coming here, it is, you can approximate that this will be 6 volt. So, in summary, if I consider this is 10 mega ohm and the equivalent resistance of this part, it is 10 mega ohm, and the ideal current here it is 2 milliampere, this is also 2 milliampere. So, then this voltage it will be 6 volt. In fact, this 6 volt, of course, we do have some assumptions, and so there is there may be a scope of debates whether those things are correct or not, but whatever it is, we do have this voltage, it is maybe in the near vicinity of 6 volt, keeping transistor 2 as well as transistor 1 in active region of operation. So, we can say that for all practical purposes, both the devices are in good condition, and hence we can move to small signal equivalent circuit. Now, before we go into the small signal equivalent circuit, I like to recall that value of GM1 and GM2 both are 1 by 13, then RO1 and RO2 both are 50 K, and R pi of transistor 1 it is 1.3 K, and R pi 2 on the other hand it is 2.6 K, right. So, with that if I try to see what is the voltage it is coming here in the small signal equivalent circuit. So, suppose we do have VB voltage here. So, the current flow here it is GM1 into VB. Now, this current it is coming from RO1. So, part of the current it is coming from RO1, then we do have R pi 2, and also we do have this circuit supplying the current, and based on this current here we do have the current flowing through R 3. So, to find the value of this current flowing through R 3, we need to know what will be the relative value of this resistance, we need to find what will be the resistance coming from this circuit and also this RO1. So, we already have the numerical value of R pi 2 and RO1, but then let us see what is the equivalent resistance coming from this circuit. So, this R equivalent, as you may recall, this is R 3 plus RO2 divided by GM2 and then RO2 plus 1. So, R 3 it is quite high compared to RO2, and this part it is quite high compared to 1. So, we can as well consider this is R 3 divided by GM2 and RO2. In fact, if you put the value here, namely 10 mega ohm 10 to the power 7 divided by GM2, which is 1 by 13, and then RO2 it is 50 K, 5 into 10 to the power 4. So, that gives us 2.6 K ohm. In fact, that is how I have picked up the value. So, this R equivalent it is same as what is the numerical value we do have for this R pi 2. So, compared to these two resistances, this resistance and this R equivalent, if I ignore, if I consider this resistance is quite high. So, you can say half of this current it is flowing through this part, and the other half the current is flowing through this R pi 2, and hence this current flow through the R 3, which is I R 3 is equal to half of GM 1 into R V B 1. So, that gives us the output voltage V O equals to minus R 3 into this I R 3, which is GM 1 by 2 into VBE 1. In fact, that gives us VO divided by VBE equals to minus GM1, it is 1 by 13, and then we do have 2 in the denominator, and numerator we do have 10 power 7. And in fact, this value, if you see, so we do have, so if you calculate this value, it will be coming roughly minus 384,615. It is a big number, right. You may recall, compared to the normal CE amplifier, the gain it was just 204. So, compared to that, this is very high. The basic basic philosophy how we get this gain, it is even though we do have very high resistance here of say 10 mega ohm, we are able to successfully flow this at least half of the current through this resistance. As a result, it is developing a large voltage. So, once we have this voltage gain, then of course, the main advantage it is very clear, but of course, we have to keep in mind that the moment we increase this resistance, that also have increased this resistance, namely 2.6 K, and incidentally that also has increased the Miller factor coming for this C mu. And what is the consequence? The corresponding C in got increased. So, the C in got increased because the Miller factor of the C mu got increased now. So, yes, we got the advantage, but we need to really calculate whether we made some significant amount of damage on the upper cutoff frequency defined by the input capacitance C in and RS and Rin. Okay. So, RS and Rin we are taking same. In fact, Rin it is also defined by R pi 1. So, RS in parallel with Rin same as earlier case, namely 650 ohm, but then we need to see what is the corresponding C in. So, to get the C in, we need to know what will be the gain from the base terminal here to the collector terminal of transistor 1. Okay. So, please try to recall all these numbers and I am going to create the space for that analysis. So, what we have said that this R equivalent coming from this part, it is 2.6 K, and also we do have 2.6 K here. So, that gives us the total resistance, these two together, it is giving us the total impedance for the lower transistor Q1. So, these two resistances together, it is giving us 2.6 K in parallel with 2.6 K is equal to 1.3 K, right. So, if I consider the base to collector gain, which is essentially if I say that VC 1 by VB 1 equals to minus GM 1 multiplied by this resistance 1.3 K in parallel with this R O 1, which is 50 K. Okay. So, roughly we can say that this gain, so this gain you can say that you can drop this part, we can retain this one, and this GM 1 it is 1 by 13. Here we do have 1300 So, if I drop this part, the gain it is becoming minus 100. So, what is the conclusion here? That the gain earlier here to here, the gain it was just 1. Now, that gain it got increased to 100 magnitude wise. That is mainly because this R 3 it got increased from 2.8 kilo ohm to 10 mega ohm, right. So, the input capacitance it is C pi of transistor 1 plus C mu multiplied by 1 plus this 100 gain. So, that is becoming this is 5 and this is 10. So, we do have 505 here and then we do have 10. So, 515 picofarad. As a result, the upper cutoff frequency defined by R s and R in, it is 1 by 2 pi R s in parallel with R in and then multiplied by C in, it becomes quite significant. So, let us I do have the calculation for you. So, we do have 1 by 2 pi 650 and then 515 multiplied by 10 to the power minus 12, and that gives us 475 kilohertz. And earlier we already have said that the pole coming from the CL and this RO, earlier it was quite small, but of course, now this output resistance it is also getting increased, because the resistance lower side it is 10 meg, upper side it is 10 meg. So, then total resistance here it is 10 mega ohm coming in parallel with 10 mega ohm. So, that gives us 5 mega ohm. So, now the alarming situation we do have here, it is 5 mega and CL equals to 100 picofarad. So, that defines the upper cutoff frequency. In fact, the corresponding upper cutoff frequency defined by this load capacitance, which is 1 by 2 pi into 5 into 10 to the power 6 multiplied by 100 picofarad. So, that is 10 to the power minus 10. So, what we have here, it is 7 3 10 to the power 3 by pi. Okay. So, that means this is roughly 300 hertz only. Yes. So, the advantage here what we got, namely we got very high gain from this circuit, which it was I think we already have said that 3.8 the overall gain, it was 3.84615. In fact, if I consider this attenuation, this divided by 2. So, that is the gain, overall gain. It is very good thing, but unfortunately, this output resistance got increased, and the corresponding upper cutoff frequency it is the concern. But of course, you have to keep in mind that while we have increased this one the gain, though the Miller factor affecting the C mu increases the C in, but the corresponding upper cutoff frequency is it is not limiting factor for defining the bandwidth of the circuit. Rather, the problem it is elsewhere, and this problem, this output resistance, it is quite high, that can be handled differently, namely by placing one buffer circuit here, which we have discussed earlier. We can put a buffer circuit here constructed by maybe common collector stage to address that. So, I should say the cascode amplifier alone is not the solution. We need to put the CC stage, but it is important to make a note that cascode amplifier, it is having two important potential. It is having the capability to increase the gain by whatever the gain we obtain there, maybe square of that, almost square of that. Also it is having the capability, in case if you are not looking for high gain, it is having the capability to decrease the input capacitance, keeping the Miller factor they are small, and hence it can be considered for one candidate to extend the bandwidth, but you need to know the situation of yours, and then only you can deploy it. Okay. So, so far we are talking about cascode amplifier using BJT. Similar kind of circuit can also be analyzed. In fact, this is what we were talking. So, in case if you are considering the CE amplifier, the CE amplifier, and then if you compare this circuit directly, it will be difficult to compare because this resistance it is high, but then this resistance you cannot make it so high. In case if you are making this is high, of course, then here the output resistance it will be defined by RO of the lower transistor. Of course, that will also affect the upper cutoff frequency, but the way this circuit has affect the upper cutoff frequency, it is quite severe compared to this cutoff frequency. Namely, for this case, the upper cutoff frequency it is if I make say this circuit replaced by this kind of active circuit for fair comparison, then the gain here it is GM1 RO1. So, this is the voltage gain for simple CE amplifier, and the upper cutoff frequency on the other hand it is 1 by 2 pi RO, RO1 in parallel with very big resistance. So, that can be ignored, multiplied by CL. On the other hand, for this circuit the gain we obtained there it was quite high, it was in fact GM1 multiplied by this R3 in parallel with whatever the resistance we obtained here. So, the resistance there it is GM2 RO2 multiplied by R pi 2. In fact, you can say that GM2 and R pi 2 it is nothing but the beta of the transistor. So, this is the gain. This gain we are talking about the gain from this point to this point without considering RS, and this is becoming GM1 multiplied by R3 in parallel with beta of transistor 2 into RO2. So, while this cascode structure it is helping us to increase the gain, to get the advantage of that in the cascode structure it is helping us to increase the output resistance by a factor of beta of the cascode transistor. To get the advantage of that on the gain, if you take this R3 also in the same order, then only it is meaningful. And if in this numerical example we have considered that this resistance it is in this order, and hence it is having a capability of generating a gain which is GM1 multiplied by beta 2 RO 2 by 2. So, assuming that these two are equal, so that is why you do have factor of 2. On the other hand, here the gain it is GM multiplied by RO 1. So, the difference if you compare difference of this equation and this equation, if you see here beta by 2 is the factor by which you can enhance the gain. So, theoretically you can say that gain of this cascode amplifier compared to similar kind of CE amplifier, it is a factor of beta by 2. On the other hand, of course, the output resistance, since this output resistance got increased, its cutoff frequency it is 1 by 2 pi. The corresponding output resistance, it is parallel connection of R 3 and beta into R O. And again, if I consider this R 3 in the order of beta into R O, so we can say that this is beta into R O by 2 multiplied by C L. Now, again if I compare the upper cutoff frequency here and upper cutoff frequency here, so you can see that the difference here it is beta by 2, but in this case cascode circuit it is having worse performance than the CE amplifier. So, and the degradation here, of course, it is the same factor by which here the gain it got increased. So, if I pictorially if I compare, if I am having the CE amplifier gain say like this, and then it is having the corresponding 3 dB frequency or the bandwidth defined by the expression there. So, this is for the CE amplifier. On the other hand, if I consider the cascode amplifier, where the gain it is quite high and then the corresponding cutoff frequency it is lower. But then if you see that the roll off here, they are finally coinciding. So, this pink color it is the performance of the cascode amplifier. So, if I consider the output node and the difference here of these two circuits, then for one case the gain it is increased, but then bandwidth got decreased. On the other hand, by the same factor for normal CE amplifier the gain is lower, but then the corresponding bandwidth is higher, and gain bandwidth product it is remaining same. It is intuitively it is also clear that by cascode structure we are essentially changing the output resistance R out, and the consequence of increasing the R out is that one is increasing the gain and then with the same factor decreasing the bandwidth. As a result, the gain bandwidth product for both the circuits remaining the same. So, that is about the cascode amplifier. So, depending on our application, if we are looking for very high gain, but then we can if we are we can tolerate with lower bandwidth, then we will be going for cascode amplifier. Similar kind of circuit it is also done for the MOS counterpart, and the value of different bias circuits are given here. Device parameters are also given here. So, we do have the device parameters are given here. For both the transistors, we consider transconductance factor, it is 1 milliampere per volt squared, lambda it is 0.01 per volt, threshold voltage of both the transistor it is 1 volt, supply it is 12 volt, and then R 1 and R 2 this potential divider it is such that it creates a voltage here it is 3 volt from this 12 volt. On the other hand, R 3 and R 4 it is creating 6 volt here. So, since the size of both the transistors they are equal and VTH is also equal. So, we are expecting both the devices they will be having equal current. So, naturally the VGS here and VGS here we are expecting they should be equal. So, we do have yes, we do have 6 volt here, we do have 3 volt here, and so this is also 3 volt. So, that gives us this is equal to 3 volt. In fact, if you see this node it is 3 volt, still this device it is in saturation region, because if the gate voltage is 3 volt, its drain voltage it can go lower than its gate voltage by an amount of 1 volt. So, the lower limit of the drain voltage of transistor 1 it is actually 2 volt. So, definitely transistors 1 it is in saturation region. Now, to start with, of course, if we have say this current this VGS it is say 3 volt, the corresponding current IDS 1 equal to IDS 2 equals to 1 milliampere per volt square by 2 into 3 minus VTH is 1 square. So, here again it gives us a current of 2 milliampere. So, this 2 milliampere it is creating a drop across this R 5 which is 2 K. So, this is 4 volt. We are assuming that this is 0, and so if we have this drop 4 volt. So, the voltage coming here it is 12 minus 4. So, that is 8 volt. Again transistor 2 it is in saturation region. So, with this of course, we got appropriate operating point of both the transistors. Now, small signal parameter wise we can calculate GM 1 equals to GM 2, and their values are 2 milliampere per volt. R O 1 equals to R O 2, which is essentially 1 by lambda into the corresponding current 2 milliampere, and that gives us again 50 kilo ohm. So, from that probably you can find what will be the corresponding voltage gain. The analysis, small signal analysis here it is very similar to the previous case. I should say rather it is simpler compared to the previous case, and by analyzing that you can find the gain. So, let us see in the next slide about the equivalent circuit here, and from our previous analysis we see that GM 1 equals to GM 2 equals to 2 milliampere per volt, and RDS 1, notation here we are using RDS. RDS 1 equals to RDS 2 is equal to 50 K, and the of course, we do not have the R pi here. So, the circuit, that is what I said, that the circuit is simpler, and at this node of course, we do have the capacitances. For gain of course, we can ignore that. So, if we have say VGS applied here, we do have GM 1 into VGS 1, and part of those that current it is flowing through this, and also the other part it is flowing through this device, and this current it is coming from this R 5. So, the again based on the relative value of this resistance and this resistance, we can say that major part of this current it is coming from here, because in this case the R equivalent it is essentially 1 by GM 1 rather GM 2 which is GM2, it is 1 by GM2, it is 500 ohm. Okay. So, it is of course significant, but still it is much smaller than this RDS 1, which is 50 K. So, we can say that the current flowing through R 5, which is denoted as say I R 5 equals to approximately equal to GM 1 into VGS, and then the corresponding output voltage VO equals to minus R 5 GM 1 into VGS 1. So, that gives us the gain starting from its gate to the output. It is VO divided by VGS 1 equals to minus GM 1 into R 5, and GM 1 we have obtained 2 milliampere. So, 2 milliampere multiplied by 2 K. So, that gives us a gain of only 4. As expected, MOS transistors they do have 4 GM. So, that is why you do have low gain. So, in case if you really want to use MOS transistor for amplification, probably we can look for cascode structure, and for that we can increase this resistance. We will see that, but before we go into that, let we also discuss that the input resistance here, since it is infinite, even though in presence of this R s, we can say that there is no attenuation. So, whatever this minus 4, it is also giving us the overall gain. So, in fact, I should say that V O divided by V in, it is same as V O divided by V G S 1, and hence this is also equal to minus 4. Now, next thing is that what is the gain, what is the, what is the input capacitance. So, let you also see the input capacitance. C in equals to C G S. So, C G S in parallel with C G D multiplied by whatever the gain we do have. So, we do have the C G S 1 plus C G D multiplied by 1 plus the gain coming from gate to drain of transistor 1. Now, here if you see the gain in presence of R equivalent, which is 1 by GM 2, and since this GM 2 and GM 1 they are same, we can say that this A V 1 equals to, in fact, I should say this is minus. So, minus GM 1 divided by GM 2, and that is minus 1. So, with this the C in we are getting C G S plus C G D into 2, and hence again here we are getting 20 picofarad capacitance. Now, this 20 picofarad capacitance, it may create a pole with this R s. So, depending on this value of this R s, it may be having its corresponding pole location. Again the analysis it will be similar. So, we will not be going into that discussion. Just we like to say that because of the cascode structure, since the C G D here it is not exposed to the output node, and hence the Miller factor for this C G D it is small. So, the input capacitance is remaining low. So, for high bandwidth application, of course, this is having some advantage. Now, next thing is that what you are looking for is that if you want to enhance the gain instead of 4, if you want to enhance the gain by using this cascode structure, what we have seen for BJT version, that this passive element probably we can try to replace by active circuit, where we can try to take high value of this R5 and then the corresponding I bias. So, I will be going to that discussion, but let me take a again short break and then we will come back with that numerical problem.